Hello.
How do you know that the 2s2 and the 2p2 are both the outermost orbitals? Because isn't 2s2 full?
Yep. But it's full, but it's kind of on the outside. The valence electrons are going to be the ones in the orbitals with the biggest big number in front. Right? So here we've got orbitals with a big 1 in front of them and orbitals with a big 2 in front. And so 2 is the biggest number. So the valence electrons are the ones in all the orbitals with the big 2. If that went us through as far as 3s and 3p, then they'd be the valence orbitals. Yeah? The valence electrons, sorry. Yeah?
So is both between carbon are they both orbital 2, or are there 2 orbitals 2?
The 1 and the 2 refer to how big they are. Right, so at this stage, it's probably enough to say that 2s is bigger than 1s. And the difference between 2s and 2p probably isn't too important for the moment. Right? Just that they're bigger than anything with a 1 in front of them. Yeah? Yeah?
So what happens when you get to 3D? Because you got the 3, which is smaller than the 4s. Does it just, is the D the valence orbital, or is the 4s the valence orbital?
It turns out that it's going to be the 4s. But if you have an atom, say you have nickel, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8, no, 3d, yes, 3d8, then their type of bonding is different. And so, well, it's, and we're going to touch on it at the end. It's still covalent, but it's different because once you get to the so-called transition elements with the d orbitals, then everything becomes a little bit more complicated. It's the same basic idea, but working out which orbitals you use and which electrons you use is a bit more tricky. Yeah. Okay. So, if we're going to draw a little Lewis dot diagram for one of these, then we go like this. The carbon has 4 valence electrons to share with the hydrogens to form covalent bonds, right? So we can draw a C and we can put 4 dots around it, like this, representing those 4 electrons. And then here are our hydrogens. We've got 4 of them. Each of them have 1 electron to share, so we could match them up, right? The hydrogen with 1 electron matches up with one of the electrons on the carbon. And so that means you're going to have a situation like this, where you have 4 lots, 4 instances where a carbon is sharing a pair of electrons with a hydrogen. And so that means you can make 4 covalent bonds. Does this make sense? And so you may have come across somewhere along the way this idea that carbon can only ever form 4 bonds. Yeah? This is why. Because carbon has 4 valence electrons, so that's all the electrons it's got to make bonds with other things. Note that the carbon now has a share of 8 electrons. So what we've done is we've made a molecule where around the carbon there are 8 electrons. Now sure, it's sharing them with the hydrogens, but it has around it 8 electrons. The hydrogens have a share of 2 electrons each. Now if you think about it, that now means that their valence orbitals are full. Now if you accept that the sharing electrons means that they're kind of helping to fill up the orbitals on the hydrogen and helping to fill up the orbitals on the carbon, then remember, if you have the carbon has got 2s and 2p, and so there's a total of 8 electrons that you need to fill up those orbitals, the 2s and the 2p together. And by doing this, the carbon now kind of has 8 electrons around it. The hydrogen has an electron configuration of 1s1. It needs one more electron to fill up that and make that orbital happy. And so it's kind of doing that as well this way, by sharing the second electron from the carbon. And so by doing this sort of thing, the atoms are able to kind of fill up their valence shells. And so it makes them happy, like we talked about the other day. And this is one of the very strong drivers for how bonding works and how indeed molecules are put together. Atoms will interact with other atoms and make covalent bonds so as to try and fill up their valence orbitals in some way or other. And this is given a name. It's called the stable octet rule. So octet refers to 8 electrons. And so stable octet rule is just saying that atoms will try and make themselves into molecules so as to get 8 electrons around themselves. Unless you're hydrogen, in which case you only need 2. But normally you need 8 because you want to fill up the 2s and the 2p, or the 3s and the 3p, or the 4s and the 4p, to fill up those valence electron orbitals. Yeah? So the stable octet rule is something which you come across a lot. Now, like all chemistry, that's a perfectly valid rule until it breaks down, and there are lots of molecules for which it doesn't apply, but there are an awful lot of molecules for which it does apply. So it's a good sort of starting idea when you're trying to work out how molecules work. Okay. Now, another one. Let's consider water, H2O. The electron configuration for the H is still 1s1, so we still kind of know where we are with hydrogen. It's got 1 electron. The electron configuration of oxygen is 1s2, 2s2, 2p4. So that means that oxygen now has how many valence electrons? 6. The 2 in the 2s and the 4 in the 2p now together make 6 valence electrons. Again, the hydrogen has only got 1 electron, so it can share an electron with the oxygen to make a covalent bond. There's 2 hydrogens, and so the oxygen only needs to use 2 of its valence electrons to make these covalent bonds to the hydrogens. Yeah? It needs to share 1 of its electrons with 1 of the hydrogens and 1 other one with the other hydrogen. But unlike in the case of the methane, where all of carbon's electrons were used for making bonds, in this case it's different. Only 2 of them need to be used. Right? And so the picture we draw is going to be a little bit different. We draw a picture like this, where here's our oxygen, and here's its 6 electrons, and what we do is we draw 2 of them by themselves. These are going to be the ones that we use to make the bonds to the hydrogens, so we can draw the hydrogens in, like that. The other 4 electrons that you have on the oxygen, we're going to draw as 2 pairs, because electrons like being in pairs. You might worry that they repel each other, but nonetheless they like being in pairs. Right? So we draw those as 2 pairs up there, and then we have these 2 other electrons which we're going to use to share with the hydrogens to make these covalent bonds. And so we can draw a picture like this, which then turns into a picture like this. Right? So the lines refer to a pair of electrons which are being shared to form a covalent bond. But in this case, the oxygen has 2 pairs of electrons left over which aren't involved in making bonds. They're just there. Right? So here's a little picture again. And so in this picture, we can see that we have two different types of electron pairs. We've got electron pairs which are being used to make bonds. And so imaginatively enough, those are called bonding pairs of electrons. So those are the ones that we've now drawn and we place as dots with the little lines, right? So the electron on each of the hydrogens and two of the electrons on the oxygen are being used to form bonding pairs and form covalent bonds. The remaining two pairs of electrons that aren't being used to form bonds that the oxygen has are given a different name. They're called lone pairs. All right, so in methane and in hydrogen, all you have is bonding pairs of electrons, but in a molecule like water, you also have lone pairs of electrons. And they're quite different, and they give the molecule quite different properties. There you are. Lone pairs of electrons can play a very significant role in determining the chemical properties of a molecule, and we will return to them shortly. And then if we go to there, or maybe we'll do one more slide, and then we'll go for biscuits. Oh, actually, two more slides, sorry. Okay, so we have bonding pairs and we have lone pairs. And obviously, how many lone pairs and how many bonding pairs and stuff we have will depend on which atoms we're using in our molecule, right? But you should also note that this oxygen still ends up with a share of 8 electrons. It's got 4 just for itself, and then it's got 4 that it's sharing between itself and the hydrogen. So the stable octet rule still applies here, right? Okay, now, oh. Okay, so a while back I said that there were two different types of bonding, but in fact in reality they were extremes of a continuum. So if you think about it, what we've got in the case of a covalent bond like we have in methane, or especially in H2, is we have two atoms the same, which are sharing a pair of electrons between them. In an ionic bond, we have a case where we have a cation and we have an anion. Now the cation has got to be a cation because it started off being an atom, but somehow it's lost an electron. Yeah? The anion got to be an anion because it started off being an atom, but it got an electron from somewhere. Right? And so if you consider the case where the anion gets to be an anion because it took the electron off the thing that now is the cation, then you have a case where rather than the electrons being shared between the two atoms evenly, you have the case where one of the atoms has completely taken an electron off the other to generate ions, which are then held together because of the charges. You see that? Yeah? And so they're kind of extremes. In one case, there's no electrons being taken from one thing to the other at all, and they're just very happy to share, right? And in the other case, you've got one thing which has completely taken the electron off something else, and then they're being held together by the charges that result from that. And it turns out that, in fact, there's a continuum, right? It's not one way or the other. There's a continuum between those two things depending on which atoms are involved in the bond. And so an important point to make here is that when a covalent bond is formed between two different atoms, the electrons in the bond are not always shared equally between the two atoms, right? In H2 they are because the atoms are the same. But if the atoms are different, then you don't get equal sharing. And in an extreme case, you don't get any sharing at all because one of the atoms takes the electrons completely for itself. And you get an ionic bond. Yeah? Actually, sorry, just bear with me for a second. Right. Maybe we'll just do this and then we'll go. And so in order to work out whether the electrons are going to be shared equally or not, or whether they're going to be more preferred to be grabbed by one of the atoms in the bond than the other, we have a number that we can use, right? Good science, we can put numbers on everything. And so the number in question here is something called the electronegativity, which is a property of the atoms in your molecule, right? And it's quantified by a number, and that number gives us a clue as to whether the electrons are evenly shared between the two atoms in the bond or whether they're not, right?